Assalamu alaikum. I welcome you all in the second course of the power system. We had already covered the power system first, in which we covered the introduction to the power system, transmission line parameters, performance of the transmission line, corona, insulated cables, and insulators. Now, in this course, we'll be discussing the purgent system, transients in the power system, faults, and in the faults we might have symmetrical faults, unsymmetrical faults, power system stability, and load flow studies. So these are different contents that we are going to cover in power system second. Now the recommended books, which book you will be referring to. The first one is the power system analysis by Granger and Stevenson, electrical power systems by VD and Corey, power system engineering by Nagarath and Kothari, and electrical power system by CL Vajra. I think I have already given these books to you, I mean ebooks. Now coming to the general introduction, I'll first introduce the fault. As I told you that I will start from the uh, as I told you, I will start from the this Punnett system. So I will give you a little bit introduction about the fault analysis, and then I will come back to this. First, I will define what is a fault. A fault is nothing but an abnormal condition which results in a stoppage of power flow from generation to load. It's actually an abnormal condition that is to be kept in mind. This is the layman type of this definition, where we can say that whenever any abnormal condition occurs that results in stoppage of power, we say that it's a fault. So in proper manner, we can say that a fault in a circuit in any circuit is any failure which interferes with the normal flow of the current or power from generation to load. This is again the same thing but in a proper way. So it is nothing but any condition and any undesirable condition which results or which interferes with the normal flow of power. So there are mainly two types of faults. We have series fault and shunt fault. And in these, shunt faults are considered to be more severe as compared to the series fault. Shunt fault results in the increase in the fault current, and series fault results in the increase in the voltage. In case of series fault, we may have, actually it is nothing but the open uh, circuit that the conductors may get open due to the fault, and we may have one or two conductors open, which results in the series fault. Shunt fault, it may be like this. We may have, since we have three phases A, B, and C, and all the three phases gets connected to each other. They are short circuited to one another. We say that that type of fault is known as triple L fault. Or all the three phases are connected to each other and also ground is involved in this. We say it is a triple line to ground fault or LLLG fault. Similarly, if a phase A and ground is connected, or if phase A has touched with ground, we see that as a single line to ground fault. In that case, we can say it is LG fault. It may be this line may be A, phase B, or phase C. Similarly, we may have a fault between two lines, two phases, AB, BC, or CA, or two lines and ground, that is AB ground, BC ground, CA ground. The frequency of these two, that is LLL and LLLG, are known as symmetrical faults because they result in the current which are symmetrical, which are balanced. The frequency is only 3%, very small percentage. The single line to ground fault has a frequency of 85%. Line to line fault has a 5% frequency, and double line to ground has 7% frequency. So in this case, you will see that most of the fault that occurs are line to ground fault. And the least severe, least frequent fault is a symmetrical fault or triple line to ground fault or triple line fault. Whenever there is an insulation failure of an equipment in a power system or a flash over of the lines initiated by the lightning stroke, a heavy symmetrical short circuit current flows in the system. This is actually the cause, or we can see the reason, of triple line to ground fault or triple line fault. It results because of the insulation failure, because we have actually an insulation between the three phases. If that insulation fails, we may say that all the three conductors will come in contact with each other, which result in the three-phase short circuit or symmetrical short circuit. Similarly, this can be done by the lightning stroke. It directly falls on the transmission line, and the air between the conductors, which acts as an insulation, it breaks down because of the lightning. Because lightning has high voltage, the breakdown strength of the air is only 30 kilovolt per centimeter. When that happens, this air breaks down and it makes a conducting part between the conductors, and three-phase short circuit takes place. Now, the main objective of the fault analysis is to determine the fault level or fault MVA at the fault location. This fault MVA is the breaking capacity of the circuit breaker that has to be kept at a point of fault location for disconnecting the faulty part of the system. As we know, we cannot mitigate the fault, but at the fault time, we can introduce a circuit breaker that opens the circuit so that the fault is not fed from the source, or we can say the fault may be cleared after that. So to install a circuit breaker, we need to first calculate its breaking capacity or fault current carrying capacity before installing it. Because if we use any circuit breaker which may be underrated, it may be damaged by the fault current. So the prime motive of the fault analysis is to design a circuit breaker at any point where the fault occurs, so that when the fault at that point occurs, that circuit breaker should sustain that fault. Now the order of the severity. Severity means how much fault current a different fault has. Since we have mainly four types of faults, it is three-phase faults, double line to ground fault, line to line fault, and single line to ground fault. Three-phase fault is in general considered to be the most severe fault because the current that flows in a three-phase fault is the highest, and after that is double line to ground fault, and then line to line fault, and the last one is line to ground fault. This is the case of almost 95% when the severity is to be checked. Sometimes there may be some exception, we will discuss that also. Or we can say the symmetrical fault gives more severe duty on the circuit breaker. That means symmetrical fault has got more current, and it makes this circuit breaker to have more severe duty during this type of the fault. Now we'll discuss a little bit about the transients on a transmission line. We can model the transmission line by a simple RL circuit. Its source is a voltage source, AC voltage source, root 2 V sine omega t plus alpha, where alpha is nothing but uh, its angle with respect to some reference, and this time this voltage source is leading by an angle alpha to some reference. So here we have assumed C to be negligible and the system is unloaded. There is no load at the time of the transient, at the time of the fault. This means it is directly connected to this, or we have a fault. But first we are assuming that the system is unloaded, that means there is no load, there is no fault. And when the transient occurs, that means this point is connected to this. That is what this means. And when it's shown like this without a straight line, it means it's a fault, it's an undesirable condition. So writing the differential equation of this circuit, it is IR, that is voltage drop across this resistance, LdI by dt, voltage drop across this inductance, will be equal to the source voltage that is given by this equation. Where in this case, this Z will be equal to the omega L square or XL square plus R square का whole square root, and theta impedance angle will be equal to tan inverse omega L by R. In this case, you will see that since we have to see the behavior in the transient, so we have to calculate the transient current. So this total current will be equal to this steady state current plus transient current. We know that this steady state current will be equal to root 2 V by Z sine of omega t plus alpha minus theta. If you remember, if we write it in terms of this phasors, it will be simply this V is the RMS value of this, V divided by Z at an angle of minus theta or alpha minus theta, because this current will be lagging to this voltage by an impedance angle theta, that is tan inverse omega L by R. That is why we have introduced theta over here, minus theta, and current will be simply V by Z, that is root 2 V by Z, rest is same. But this will be equal to A e raised power minus t by tau, that is the transient part, where A is the magnitude of the transient at the starting. So it can be calculated. As we know, this is an open circuit. At t is equal to 0, there will be no current. At t will be 0 plus, there will be no current because of the inductor. Change of current will be 0. So we can use this initial condition to calculate this A. At t is equal to 0, it is equal to 0. That means this is equal to 0. This also equal to 0. That means this A will be equal to minus root 2 V by Z sine of alpha minus theta. Or we can take this minus inside, or this A is equal to root 2 V by Z sine of theta minus alpha. So that has been written over here. You can see e raised power minus t by tau, where tau is the time constant of the circuit, which is equal to L by R. Now the maximum momentary current will occur. Maximum momentary current will occur when this has a maximum value. This has a maximum value when omega t minus alpha minus theta will be equal to pi by 2. That is the peak of the AC voltage, AC current. It will have a maximum value at that time. So I have written it here like this. That is like this: root 2 e by z sine of omega sine of theta minus phi, and this will be at t is equal to 0, because as t approaches to infinity or t goes to a finite value, as t increases from 0, this term will vanish. This will have a maximum value at t is equal to 0. We want to find out the maximum value, and the maximum value will be of this transient part will be at t is equal to 0. And if it is possible that the value of this steady state part is also maximum at t is equal to 0, this will be the maximum value. Then this one will be the maximum value of the short circuit current. So if we assume that XL is greater than R, which is actually the case, in that case theta will be very close to 90 degree. So this sine theta minus alpha will be equal to cos of alpha. So Imax will be equal to root 2 V by Z plus root 2 V by Z cos of alpha. If alpha will be equal to 0, this will be 1. So it will be equal to root 2 V by Z short circuit current when the voltage wave is going through the 0. It is known as doubling effect. It is known as doubling effect. So its value is equal to 2 root 2 V by Z. That means when alpha is equal to 0. Alpha 0 means when voltage wave is going to 0, our reference point is exactly the 0 of the voltage. So in that case, we can say short circuit operating voltage is going through the 0. It is known as doubling effect. So I want to have some certain observations regarding this. For that case, I have, so when the circuit breaker is designed, we have to take this maximum current into consideration. So if we make the mechanism in such a way, we can mitigate this current. You can say this is root 2 V by Z sine of theta minus alpha. We can make this equal to 0 if theta is equal to alpha. So what I mean to say is that if alpha, that is the switching time, or we can say the leading angle of the voltage with respect to reference, if it is made to be equal to the impedance angle of the system or network, in that case this transient part can be made equal to zero. In that case, the circuit breaker which is designed has to only pass the steady state current. There will be no transient current. So the transient part in equation can be made equal to zero if theta is equal to alpha. That is, the switching is done when the wave passing through it is tan inverse of omega L by R. That is simply the this impedance angle. In this case, switching means opening of the circuit breaker. Now, one more observation. On the other hand, if alpha minus theta is equal to minus pi by 2, or theta minus alpha is equal to pi by 2, the transient will have its maximum value, and the first peak of the resulting current will be twice peak of the value of the sinusoidal steady component. That means if this value is equal to pi by 2, theta minus alpha is equal to pi by 2, this will have a maximum value. If this has the maximum value, that's almost this will go to this value, 2 times of this. So to avoid this, we'll never switch this circuit breaker, will never open the circuit breaker at the peak of the voltage. That means theta minus alpha is equal to pi by 2. We'll always switch it at alpha is equal to theta, so that this momentary current or transient current will be equal to zero. This part, that means to make the transient part is zero, is only available in case of AC. We don't have such privilege in case of DC. So I will stop here, and I hope that you understood this. If there is any problem, please let me know.